Hello? Yeah, okay. Hello? Oh, okay. Fine. Ah, hello? Okay, fine.
Okay, so we are going to continue with our next talk, which will be on best of both worlds, revisiting the Spy Master's double agent problem.
So, hello, I am Anushwa, and this is joint work with my PhD advisor, Karmeet, and our collaborators, Muthu and Oksana. In this work, we introduce a new notion of secure multi-party computation. We call it MPC with fallback security. So let me first motivate the setting. So consider a scenario where a lot of countries or organizations want to come together and securely collaborate. They want to get their desired outcomes from this, but at the same time, they don't want to leak any of their sensitive information. And well, MPC protocols already exist for this, and we could just end the story there. But uh, well, current MPC protocols also have their limitations. So now, what would happen if, say, some of these people want security in the presence of uh, a lot of not so powerful people coming together and colluding, while others want security when very few very powerful parties collude. Now, when people want different things like this and there is no one middle ground that can handle both security concerns, they could never collaborate. And we don't want this. We ideally want to achieve both. So here's another scenario. We have MPC protocols today that work just fine, and some of them are even deployed in practice. And they work just fine, and they run over the internet, and they're secure now because, well, they rely on public key assumptions that we know are hard to break. But what if in, say, 10 years, IBM or Google come up with these powerful quantum computers? Let's say they've been logging everything, every protocol that they've been participating in so far, and now they have enough power to just break the security of the protocols just by the transcripts that they have. And so, and this is not so nice, right? So we would want protocols with a little, well, this sense of everlasting security, right? So is there a way to make protocols that are secure for PPT adversaries that also satisfy this extra unconditional security? I mean, even if it's for a smaller adversary structure. And that's this motivating example. There's this other thing. Uh, there's this setting we call the David versus many Goliath setting. And so most of us have heard about this story about this boy who defeated the giant, right? And but what if there were many such giants teaming up against David? Similarly, in MPC, can we guarantee security for one designated weak party in the presence of an unbounded adversary corrupting, say, everyone else? Well, this setting is only interesting in the case where we have a PPT adversary that could corrupt any subset of the parties as well. Um, Now, this is a setting also considered in previous work by Chom et al., and they have semi-honest protocols for this. Now, okay, so with present day MPC, what can we do? We have protocols in which multiple parties can communicate, and they can compute basically any functionality. And these protocols come in two distinct classes. So there is this one class of protocols which is secure in the presence of an unbounded adversary, but the adversary can only corrupt a minority of the parties. And then there's this other class of protocols in which we have security when an adversary corrupts almost everybody, but this adversary can't be very powerful. It's a computationally bounded adversary. Now, most protocols today, they fall into either one of these two classes. And in particular, it is impossible to get, say, unbounded security when almost everybody is being corrupted. So what we do in MPC with fallback security is to take what we can from both these settings and put them together. So we need one protocol that is secure when an unbounded adversary corrupts a minority, and a PPT adversary corrupts any subset of parties. And this second property is what we call the fallback property. And a similar setting has been considered by David Chom, and this was called the spy master's double agent problem. So settings similar to fallback security have been considered in other places in the literature as well. So in particular, there's this whole line of work on round optimal 2PC using minimal assumptions. And they consider security for when one designated party is corrupted by an unbounded adversary and the other party is PPT corrupted. And then there is Chom's work, like us. They consider the general multi-party case. And in particular, they solve the David versus multiple Goliath scenario for the semi-honest case, but they give a protocol that has rounds, a number of rounds proportional to the computation size. And they also have this general semi-honest secure protocols, which have rounds proportional to the size of the computation and the number of parties. They look into malicious security as well, but they don't. They look at it for much more restricted classes of adversaries. Now, we revisit this problem, and here is our main result for the malicious case. So what we can do is we can compute any functionality with malicious fallback security for an adversary structure for which semi-honest unbounded secure MPC exists. So this means that our final protocol is secure when an unbounded malicious adversary corrupts anything within this adversary structure, and a PPT malicious adversary corrupts any number of parties at all. So why this works for any semi-honest adversary structure, even though there are like separation results between semi-honest and malicious secure protocols, this is because we assume the existence of broadcast and we prove security with abort only and not guaranteed output delivery. Then we are also black box in underlying assumptions, and this is an improvement over previous work. And also, we achieve optimal round complexity up to a constant factor. And in particular, our protocol for David versus multiple Goliaths is constant round for any functionality. And also, our general semi-honest protocol has rounds independent of the number of parties. Now, does the existence of fallback security solve all the problems we just talked about? Well, our feasibility result implies that multiple parties with different requirements of as to the power of the adversary can actually come together and collaborate, as long as the unbounded adversary structure is feasible, as in like what we showed in the theorem. Now, this is because we have compilers that can take any protocol that has unbounded security and compile it to fallback security. And this comes for free, essentially. Now, also, fallback security allows us to build protocols based on computational assumptions that already provide some resilience against quantum attacks. So our approach can be used to build protocols using quantum unsafe primitives that will still remain secure when quantum adversaries are considered, as long as not too many of them collude. So, and we also show that the David versus multiple Goliaths setting is feasible and fallback secure, and we have constant round protocols for this. So we're good. Okay, now let's get into our constructions. So before looking at the main theorem, we'll talk about the semi-honest fallback secure protocols. First, let's look at the David versus multiple Goliaths case. What we want here is an n-party protocol computing any functionality that is secure when a semi-honest PPT adversary corrupts any subset of the parties, and an unbounded adversary corrupts any parties, not including the last party. So this is a very specific adversary structure for the unbounded case. So as a warm-up exercise, let's see how we can do this with threshold fully homomorphic encryption. And each party has the FHE public key and an n out of n secret share of the secret key. All parties then encrypt their input and give it to the last party. And then this last party computes the encrypted output and gives it to everyone else. They all pool in their secret key shares, and then they decrypt the output, and that's the end of the protocol. So this is constant round, everyone sees. And now, what happens when an unbounded adversary corrupts any subset not including PN? Well, nothing, because it only ever sees the encrypted input and encrypted output. So even if it could break FHE, it gains no information about the honest party's inputs. I mean, except for what the output would reveal, but that's simulatable. So, okay, now what happens when a PPT adversary corrupts PN? So note that in this setting, if the adversary were unbounded, we would be in trouble, and this is totally insecure. But a PPT adversary can't break FHE, so we're good, right? So that's that. Now, let's do the same thing with minimal assumptions. And so we have our n parties, and the first n-1 parties contribute randomness, and they create a garble circuit. We know that this can be done in constant number of rounds and for any circuit with symmetric key primitives. So this garbling is given to the last party. Then each party masks its input with the color bit it used in the garbling and gives this directly to the last party. And now PN OTs with every other party. And this oblivious transfer protocol is secure against an unbounded sender and a PPT receiver. And this is a necessary assumption. So PN receives this set of labels it would need to evaluate the garbling, and then it evaluates and sends the answer back to everyone else. So now what happens when an unbounded adversary corrupts a subset of the garblers? Well, nothing again, since the garbling protocols depends only on the randomness and not on the inputs, and the masked inputs are directly sent to the honest evaluator. The OT protocols are secure for an unbounded sender, and the adversary only sees the output in the end. So there is that. Now, what happens when a PPT adversary corrupts the evaluator? Well, due to garbling security and OT receiver security, we're still good. So this is a constant round protocol for the David versus multiple Goliaths case, and we are black box in the OT and garbling. Now, let's look at the semi-honest general fallback security case. So what we do is we present a compiler that takes an n-party unbounded secure protocol and compiles it to fallback security. That is, it gives a protocol for the same unbounded adversary structure, but which is additionally secure for when a PPT adversary corrupts any subset of the parties. So for this, first, we take this virtual protocol that's only unbounded secure and write it in terms of next message functions. So we have one such function for every party for every round. Now, the real protocol, the end parties emulate this virtual protocol and one by one execute each next message function. And this is done by first having each parties have a secret share of the states of all the virtual parties. So to begin with, the inputs and the randomness of each virtual party is n out of n secret shared among all the real parties. Then for each next message function of the ith virtual party, this function is compiled and it's computed by all the real parties. And this functionality basically reconstructs the shares of the state, it computes the next message, and then it reshares the output among all the parties. And how this functionality is realized is using the David versus multiple Goliaths protocol that we just saw. And over here, the ith party is David and is the Garbal circuit evaluator. So the output shares of this functionality are used to update the shared state, and a similar thing happens for the next message functions of all other virtual parties with the corresponding real party as David. And this goes on for every round. And finally, after all the functionalities are executed, the output is reconstructed by all the parties. Okay, now what happens when an unbounded adversary corrupts a minority of these parties? So note that all intermediate views are n out of n secret shared, so it gets nothing there. So for every next message function not sort of belonging to this adversary, these parties act as Goliaths and learn nothing. However, for every such function where this corrupt party is David, the security is completely violated, right? And it's safe to say that the adversary has all the inputs, outputs, and randomness of these executions. So if real party PI is David and corrupted, then the complete view of the ith virtual party is compromised. But this doesn't help because the unbounded adversary can only corrupt those real parties corresponding to which the virtual parties it's allowed to corrupt in the virtual protocol. And this view that it sees of these virtual parties is simulatable. So we are still secure. Okay, so now what happens when a PPT adversary corrupts any subset of the parties? Well, security comes easy because all intermediate states are secret shared and all protocols, all sub-protocols are fallback secure. So there is that. So that was semi-honest security, and we'll only briefly outline what happens for malicious fallback security. So here is a good paradigm for malicious secure MPC that we all know. So you generate authenticated triples in an offline phase, and you consume it for any functionality in the online phase. And this is the speeds approach. And this is nice because the online phase is already unbounded malicious secure for any set of corrupted parties. So this reduces our problem to just creating a protocol for the offline phase. Now, for the offline phase, we'll use a variant of the IPS compiler, that is the HVW compiler, and we'll take the semi-honest fallback secure authenticated triples generation protocol. We know we can do this, and we will upgrade it to malicious security. Why this is neat is because this compiler allows us to do this in a black box way. And we won't go into the details of the protocol and its security, but roughly it follows a commit and proof paradigm where the parties need to commit to all the input and randomness used in the semi-honest protocol. Then they're forced to complete the execution semi-honestly, and because in the end, certain commitments are going to be opened and checked for semi-honest execution. And so to pull this off, we need a building block, which is an n-party commitment scheme, and we need this to be maliciously fallback secure. And we construct such a scheme, and we use it in both the online and the offline phase to get our final result. Okay, now even building such a commitment scheme in the fallback setting is hard, and this is what we'll talk about now. So our goal is to get a fallback secure commitment scheme for any Q2 access structure. And there are n parties, and one of them is the committer with the input X. The n-party commitment operates in two phases. First, in the commitment phase, the committer needs to sort of submit its input. And at this point, no other party needs to should know what the input is. And this is the hiding property of the commitment. Then in the reveal phase, all the parties receive the input of the committer. Here, the committer should not be able to convince all the other parties and open its commitment to a value that was not used in the commit phase. And this is the binding property of the commitment. So the hiding and the binding property of the commitment are quite contradictory. One says that you can commit to a value and it could be like, and the commitment could be like anything. And the other says that the value should be open to that one thing and nothing else. And now, in order to implement this functionality in the fallback setting, we need to the protocol to be statistically binding so that an unbounded corrupt committer can't cheat. We also need it to be statistically hiding so that an unbounded adversary corrupting any subset, not including the committer, can't see anything in the commit phase. And Well, although two-party commitment schemes exist, no scheme can be statistically hiding and binding at the same time, right? So further, to extend this two-party thing to the n-party case, we need to consider these other cases where the adversary corrupts the committer and others together. And we still need to preserve binding in cases like this. And not just that, we need fallback security. So we need a security when a PPT adversary corrupts anybody also. Okay, now let's see how we make this with the tools that we already have. And so here's a subprotocol. The committer creates a statistically hiding commitment of X and first broadcasts it to all the other parties. But note that we're not done yet because this is only computationally binding. And so what it does now is that it creates secret shares of X using the access structure corresponding to the adversary structure. This is the structure for which we need unbounded security. And it creates statistically binding commitments to each share, and each ith share is now sent to the ith party. And these are committed using a statistically binding commitment. And so this commitment is not statistically hiding, but that's okay because of the secret sharing. We'll get to the properties in a bit. So this is basically the end of the commit phase. Now in the reveal phase, well, the committer gives the input, all the shares, the first commitment randomness and the second commitment randomness to like everybody. And each party checks whether the shares reconstruct to the input, whether the commitments check out, and if nobody has aborted, then this was a correctly committed value. So there is that. And now this protocol can be made extractable for the PPT and the unbounded case by adding proofs and arguments of knowledge appropriately. And okay, so now let's examine the hiding and the binding properties of this protocol. So what happens when an unbounded adversary corrupts a subset of the parties, including the committer? Well, we need statistical binding, and we get this because we have enough honest parties to always reconstruct the secret share from the binding commitments and to get exactly that one value that was committed to. So there is that. Now, what happens when an unbounded adversary corrupts a set not including the committer? And in this case, we need statistical hiding, and we get it because the first commitment is statistical hiding. And although the statistical binding commitments are not, well, the adversary never has enough shares to reconstruct the secret. Okay. Now, if a PPT adversary corrupts any subset of the parties, we have hiding and binding because all commitments are computationally hiding and binding. And we're good. So this concludes the discussion for this work. And so I'll briefly talk about future work. So note that this work is about MPC, and we consider best of both worlds between unbounded and PPT adversaries, and we give protocols with security with abort only. But there is this whole other class of honest majority protocols that provide guaranteed output delivery. And in particular, there is this one line of works that look into the best of both worlds, in which for PPT adversaries that have guaranteed output delivery and security with abort. So what we plan to come up with is a protocol that can do all three up to, well, the feasibility results. That is one protocol that gives guaranteed output delivery for the unbounded adversary for a limited adversary structure, and then security with abort for PPT adversaries for beyond that and up to what is feasible. And that's all. Thank you for listening.
Do we have any questions? I was wondering, have you thought about like trying to have a compiler that starts from maybe a protocol that either satisfies the unbounded security against the unbounded adversary and trying to upgrade to your model, or with security against the PPT adversary and kind of trying to upgrade to your model? Do you think
That's exactly what we do. Our semi-honest compiler takes an unbounded secure protocol and upgrades it to fallback security.
Okay, so but
Yes.
maybe I missed that, but like, would that work with any protocol that
Yes,
is
yes,
there? Okay,
that's true.
okay, all right, great. Any other questions? Okay, let's thank the speaker again.
Beautiful. Better now? Great.
All right, so our next speaker will be Anders, and he will tell us about perfect MPC over layered graphs.
Cool. Thank you for the introduction. Yeah, so I'm here to present layered MPC, perfect MPC over layered graphs. This is joint work with Bernardo, Yuval, Eyal, Varun, Arushi, Chandar, and Giovanni. Oh, the delay here. Okay, so I'm first going to talk, give a brief motivation, then look at the definition of layered MPC, then go through a few protocols in the layered setting, and then finally some results. Okay, so we depart from the setting of BDW. Here they give us general MPC with perfect full security and optimal corruption threshold T less than N/3. And here we have a set of parties where some of them may be corrupted, and each of these parties has an input, and then the output of the computation is the function of these inputs. In 91, Ostrovsky and Young came and challenged this assumption that once a party is corrupted, it remains corrupted forever. And they came up with what's called a mobile adversary, where the timeline is split into epochs, and in each epoch, a new set of parties may be corrupted. They also showed a feasibility result in this setting with information theoretic security. Now, Herzberg and others started a line of work that proposed protocols that are secure in the presence of this mobile adversary. It's called proactive protocols. A line of work starting with this Meta Yoyoda challenged another assumption, namely the assumption that it's the same parties doing the computation for the whole duration of the protocol. And they proposed this dynamic proactive protocols where in each epoch, a subset of parties can be replaced. Now, recently there has been quite an interest in what we call MPC with ephemeral servers, and this includes Yoso and Fluid MPC. And here all parties are replaced in each epoch. And moreover, each party can only communicate one single message. Okay, so we can see this like as a wheel of time where in each step in this wheel, existing assumptions has been challenged and new protocols and models have been proposed. And now we are in the arguably most extreme dynamic setting of MPC with ephemeral servers. And we want to investigate it's possible to get the original BDW result, but in this extreme dynamic setting of MPC with ephemeral servers. Yeah, so it's possible to construct MPC with ephemeral servers, achieving perfect full security against a maximally mobile adversary while maintaining optimal corruption threshold. And here, a maximally mobile adversary is an adversary can move in each round. So why has this question not been addressed before? Well, in a setting of proactive MPC, we have the work of Herzberg and others. But in general, this line of work considers epochs that are larger than one round. Actually, the original work of Ostrowski and Young, they consider one-round epochs. They have a statistically fully secure protocol, but the corruption threshold is just a small fraction of the total number of parties. In the context of ephemeral committees, we have the recent work of the protocol that is in the Yoso paper, original Yoso paper. This has one-round epochs, statistical and full security, and it has T less than N02. But the way that these committees are sampled from a larger set, it makes it so that this threshold does not apply when the number of parties is constant. And even if it's somehow allowed for this worst case corruption in this model, then they also assume an ideal channel to parties in an arbitrary future round. We call it any future round communication. The setting of fluid has one round epochs, statistical security, but they enjoy only security with a board. And we would like to see if we can get one round epochs, perfect and full security, T less than N03, and only using next round communication. So the way we're going to attack this is using something called layered MPC. And this is an instance of standard MPC with restricted interaction pattern induced by a graph here. And then we use the setting of layered MPC to indirectly study protocols in the maximally proactive setting of Ostrowski and Young. And basically, we have this lemma that we prove in the paper that if we have a secure layered MPC protocol, then we also have a secure maximally proactive MPC protocol, assuming that honest parties can do the necessary erasures in the proactive setting. Okay, so the main contribution in this paper is we formalize this model of layered MPC. This is standard MPC with special interaction pattern and a specific adversary structure. Then we present layered MPC protocols for general functionalities with perfect and full security and optimal corruption threshold. And we have CNF-based protocols or replicated secret sharing protocols, if you will, and also a asymptotically efficient Shamir-based protocol. And using this implication I mentioned before, we then improve on existing result in the maximally proactive setting. And we also improve on the new work with the ephemeral committees. Finally, we also present a layered protocol with general functionalities in the computational setting, and here with T less than N02. Okay, so let's look at what is layered MPC. We say we have an NTD layered protocol with the following properties. So we have capital N parties divided into D+1 layers, and each layer has N parties. Then the protocol proceeds in desynchronous rounds, and in each of these rounds, the layer at hand can just only send using point-to-point channels, send messages to the immediate next layer or using broadcast. And we consider functionalities F here that takes input for input clients in green and deliver output to output clients in red here. And we consider active rushing adaptive adversaries. And this adversary may corrupt any number of input and output clients, but is limited to only corrupting T parties in each of the intermediate layers. So just a note on this layer broadcast. So we assume layer-to-layer broadcast in our setting, and this is actually somewhat necessary because we have this we prove this lemma here that deterministic broadcast is impossible in the layered setting. And this is something we derive from a result from Garay in '94. And we have this lemma: the deterministic broadcast is possible if and only if T is equal to 0 in the layered setting. Okay, so let's look at some actual protocols in the layered setting. So we start by looking at the primitive future messaging, which is the backbone of all our protocols in the layered setting. And this functionality takes a message from the sender here in green and delivers the message to the receiver in red. And importantly, if the sender and receiver are honest, then the message will be hidden from the adversary. So how do we imagine we can realize this? Well, if you just want to do it for one layer, then we can just use our point-to-point channel to the immediate next layer, and that gives us a protocol for future messaging. And for 2 layers, we just have the sender secret share its message and send these shares to appropriate parties in the next layer. And then these parties can forward the shares to the receiver in layer 2 in this case. And this party can reconstruct the message. And this is actually equivalent to what's called perfect malicious one-way SMT, which we know we can do for T less than N over 3. So what if we want to send the message to layers further away? Here we have the sender in layer 0 and the receiver in layer 6. Well, we can actually decompose this into 2 future messaging by using the same trick as before, just sending the shares to layer 3 or appropriate parties in layer 3, and then have these parties forward the shares to layer 6. And we can decompose it even more. So we can see you have this recursive way of constructing our protocol for future messaging from one layer to an arbitrary layer in the future. Now, this was all assuming that we have an honest sender. So what if we have a dishonest sender? Well, we run into some problems with rushing. And in particular, if we want to do parallel invocations of our future messaging protocol, then the adversary can do what's called a correlation attack. And basically, if you have 2 invocations of the future messaging protocol here for one layer, then the adversary can obtain the message here and use that as an input in another future messaging protocol. And we tackle this by modeling our parallel functionality as corruption aware. But actually, this issue here, it persists even beyond one layer. And this has to do with the other issue that we have, which is that our primitive is inherently non-committing. And this means that the adversary can change the message from one message M to another message M prime at any point until the very last layer before the receiver receives the message. And this is like a crucial difference from the YOSO setting, because in the YOSO setting, they assume these ideal channels to parties in an arbitrary future. And these channels are committed or committing, and we don't know how to realize those in the layer setting. Okay, so we can extend our future messaging to what we call conditional future broadcast. It's pretty easy. For future broadcast, we just take the layer just before sending the messages or shares to the receiver. We just broadcast those shares to the layer. And these shares can be broadcast conditioned on some event. And that's what we call conditional future broadcast. Okay, just summary of future messaging. So assuming we have a linear secret sharing scheme, we have this recursive way of constructing our future messaging protocol, which runs in O of n to the log d, log m, where m is the message domain. And if you have an honest sender, it just reduces to SMT. If you have a dishonest sender, then we have this challenging with rushing that we have to take into account when we design our protocols and do the modeling. And we have the extension from future messaging to what we call conditional future broadcast, which we're going to use later. Okay, so let's look at a bit more involved protocol. So we're going to create a VSS protocol based on CNF secret sharing or replicated secret sharing. And the way we're going to tackle this is first we're going to look at a protocol from DIKR. This is a VSS protocol in the standard setting. And trying to transform this into a layer setting, we're going to use some techniques and learn some techniques. And this is we're going to use in our weak future multicast protocol. This is a sub-protocol or the future multicast protocol, which is a sub-protocol of the final VSS protocol. So let's look at what DIKR can teach us. DIKR is a very arguably the simplest VSS protocol. You just have a dealer sharing its secret to the parties here, party 1 to party 4. Then because this is CNF secret sharing, these are just additive shares. So the parties that have the same additive share can exchange these shares. And if there's any disagreement, then the party will complain using broadcast. And then this forces the dealer, to resolve the complaint by also broadcasting the additive share. So we just assume now that this is a secure VSS protocol in the CNF based on CNF secret sharing. then there are some obvious challenges with putting this directly into the layered setting. First of all, the dealer speaks both in round 1 and in round 4, right? And we can tackle this by emulating the dealer using the conditional future broadcast that we saw just before. But also the PJ and PJ prime, they exchange these additive shares during the protocol, and we cannot do that in the layered setting. But instead, we can invoke what we call a distributed equality check, which is basically just an invocation of a protocol for addition, and we could do that for each pair, J and J prime. Okay, so just keep these techniques in mind, and then I'm going to present this future multicast functionality here. This is a functionality where the functionality takes a message from the sender and delivers the message to the receiving set here in red. Now, importantly, if the sender and the receivers are honest, then the message is hidden from the adversary. So then when you're going to create this future multicast protocol is by having the sender sampling additive shares of the message. And then each of these shares are sent to the receiving set using weak future multicast, which I will describe in just a second. And this is done with using a different set of intermediaries here in blue. This set of intermediaries have size n-t. Now, parties in the receiving set can just add up all the additive shares and then obtain the message. Okay, so what's left is to figure out how we do weak future multicast. So remember, we want to send one single additive share from the sender to the receivers using a set of intermediaries here in blue. So first of all, we just have the sender send the additive share directly to the intermediaries using our point-to-point channels. Also, the sender will do a secret sharing and send each share to appropriate parties in layer 3. And this is done using the future messaging as described before. Now, you can see that we can do this distributed equality check because each of these intermediaries can invoke this protocol for addition and do that for each pair. And the result will then be revealed in layer 3. Each of the intermediaries also does a secret sharing, and then using future messaging sends these shares to appropriate parties in layer 4. Oh, maybe I can use this. Perfect. Now you can see what's going to happen, because in layer 3, we have the results of this distributed equality check. And if there's any disagreement, now the layer 3 can choose to recover what's coming from the dealer, all the shares, and send these shares to layer 4. And layer 4 can reconstruct and forward the additive share that's coming from a dealer to layer 5. If there's no disagreement, then the layer 3 here does nothing. And the layer 4 can recover whatever is coming from the intermediaries here. And this is basically shares of each of the values that the intermediaries got from the dealer. So these shares are sent to layer 5. Layer 5 reconstruct the values from the intermediaries and just chooses the one that occurs most often. Now, importantly, in both cases, layer 5 here, the receivers in layer 5, they will agree on this additive share. I'm going to skip this analysis and go directly to convincing you that we go all the way to VSS. So going from weak future multicast to future multicast, we just do as we sketched before. We just send each additive share using a different set of intermediaries. Now, importantly, because at least one of these set of intermediaries are comprised of only honest parties, then this message will be hidden from the adversary if the sender and the receiver are honest. And going from future multicast to VSS is quite easy in a CNF setting, because we just sample an additive sharing and then sending each additive share to the right subset of parties in the receiving layers here, or in layer 5, and that gives us a VSS. Okay, then some results. So I hope it convinced you we can go quite far with these techniques, and we go all the way to MPC. So if you have a functionality F, computed by a layered circuit over a finite ring, and it has D layers. Then we have this NTO of D layered MPC protocol computing F, and this is if T is less than N over 3. And we have the corresponding corollary for the maximally reactive setting. So we have a maximally reactive MPC protocol computing F in over D rounds, also assuming T is less than N over 3. So this may actually be concretely efficient for small n. And we can also use techniques from CDI 05 here to amortize the communication. So basically just sending a k-bit seed and then let the receivers generate most of these shares themselves. And this, of course, makes use of a black box access to a PRG. So we end up in the computational realm or computational security. We also have the efficient theorem here. So if you have instead a layered arithmetic circuit or finite fields, also with D layers, then we have this NTO of D layered MPC protocol for F. And this is secure if T is less than N03. And this is important. This is with polynomial communication complexity. And then we have the corresponding corollary in the secure maximal effective setting. And this is just done by extending the techniques of distributed quality check and conditions of future broadcast to the BDW setting. So finally, we went through the future messaging and the VSS for based on CNF secret sharing. We also have the efficient, asymptotically efficient protocols in section 5. And finally, we have the computational result in section 6 with threshold T less than N over 2. So to summarize, we define MPC over layered graphs. We call it layered MPC. This is an instance of MPC with restricted interaction pattern and a specific adversary structure. It has implications for maximal practice protocols, the setting of Ostrowski and Young. We reviewed in this presentation a CNF-based layered protocol for VSS. In section 5, we have the asymptotically efficient protocols based on BDW. In section 6, we have the computational results with threshold T less than N02. And as future work, it would be nice if we could identify a compiler that takes a class of protocols in a standard setting and transform them into secure layered protocols, basically. Also, we would like to investigate the statistical setting and see if we can identify protocols that have threshold T less than N02, and then get a full characterization of this layered MPC setting. Thank you.
Any questions for the speaker?
Hello, thank you. I want to ask, what's the motivation in considering replicated secret sharing? Does it give you any other benefit? Because it's like these settings are inherently large number of parties. That's the only setting in which they make sense. So I'm wondering, why would you like to consider replicated at all?
So why we consider CNF or replicated secret sharing at all? Yeah, so first of all, the protocols are much simpler, right? For didactic purposes, it's easier to understand the CNF-based protocols. The other thing is that for small n, it may actually be more efficient to have the CNF secret sharing based protocols. So it's not completely subsumed by the Shamir-based protocols.
So do you have any intuition on the constants, like when it becomes meaningful to use replicated?
No. Sorry.
Thank you.
Any other questions? All right, so this concludes our session then. Thanks the speakers again.